All right, how you guys doing? Doing okay? There's a lot of people at the career fair now, so I'm happy that you guys have that opportunity. If you felt like you really need to, feel free to scoot out, catch up later on the channel. Several of you, your classmates, have already notified me of that. So if you feel like that's a big need for you, I understand and don't mind. Okay, last time we began talking about granular filtration, kind of went over the basics. Today we'll flesh that out further, and we'll probably get to membrane filtration as well, because this is a bit shorter. I got very close to finishing the grading, but I didn't finish, so I'm gonna be getting you exams back on Tuesday next week, and have also the grades posted for that probably sometime before Tuesday. So you can expect that. I think that the scores were looking a little better after the first page for many of you. I mean, some of you did fine on the first page as well, but okay, so you'll have more info on that pretty soon. We'll talk about that. I'll give you a little survey, see how you're feeling about it on Tuesday. Okay, so with that in mind, we'll kind of scoot through filtration today. We'll probably get into membrane filtration as well, but there will be some of that left for, I guess, Thursday next week, because we'll go through the exam on Tuesday. Okay, so we left off talking about, okay, when do we backwash these granular membranes? How do we know when we backwash? And I had a good question at the end of class that one of you came up to me afterwards, and I wanted to kind of speak a little bit to that a little more generally to everybody. There's a question about all this dirty water that we produce in that backwashing. We saw those videos, just nasty looking water coming out. Where does that go? Does that get sent back through the filters? Because that would just accumulate particles. How does that work? And really, we would typically send that to a different facility altogether. Sometimes maybe a water treatment plant that's treating drinking water has enough facilities and expertise to run a small wastewater operation for that as well. But typically you would send it either to the sewer system, which would cost some money for them to take that amount of load, or in some other way it would be processed. Now, there's a good chance you could sediment a lot of that because it's really, really tons and tons of particles. So it shouldn't be too hard to gather that and then squeeze out the water and have some sludge and then deal with the sludge accordingly. And there is actually typically a few processes that could produce sludge, including sedimentation. So whatever the case, we're going to have some flow of wastewater associated with cleaning our water, and that's not going to come back into the input. We're going to just deal with that separately and discharge that treated wastewater to the environment. Okay, so that's kind of a bit more context for you there. Now, determining when we backwash, we talked about this. We have 3 different limitations that we could impose, and almost always we're going to have that turbidity limit as a safeguard. So we talked about that, and we talked about how, in general, we're going to go through some rinse or ripening stage, then what we would call filtration or production. That's the bulk of our time. And then later we're going to backwash, and sometimes that includes like an air purge involved. So possibly we use air, but certainly backwash with water. Then we repeat the cycle. So that's kind of the generic cycle, and we could look at how the pressure changes over time, or over operation time. We could look at how turbidity might change and how that could inform the time frame where we say, okay, no matter what, we're cutting off after X number of hours. So that's the theme, and the question becomes, what do we do mathematically to know we've designed a plant with enough filters to accommodate, given some filtration regime and some common practice that we establish. So the question is, how much water can we produce in net? So in net meaning over the course of one cycle time, the filter is on producing water for a portion of that, and then it's off to wash, and it's taking away some of the water we just cleaned. So in all of that, we have to account for the net production in order to get a net flow rate of sorts for our design. So really, this is just a fancy way of saying, all right, let's account for the losses so that we can average it over like on a 24/7 basis, what's the average amount of water we're producing. So that's the point of the math that we're going to do pretty much. So a couple of notes here is a typical production rate, so when we are filtering, would be some flow rate that's like, I call it a flow rate. A better way to say it is a loading rate, because we are flowing it onto a certain surface area of a filter. And so the design basis is, well, how much surface area of a filter do we need? And then this flow rate becomes what we might call a flux instead of a flow rate. So you'll see these units here. Typical values would be something like 5 to 25 liters per second, but that's per square meter of filter area. So it'd be liters per square meter per second. Another way we might say that is 2 to 10 gallons per minute per square foot. So you'll see here in either way we are taking some area of our filter and we're flowing with some flow rate through it, and we're dividing that by that area. This is our loading rate. And it is essentially what we would call a flux in most scenarios. Does that make sense? Okay, so here's a couple typical values we can see. And if you think about that, every second we have 5 to 25 liters going through 1 square meter. That's not a huge speed. It's not really, really rapid, but it's not slow, right? So we can think about those examples we saw, how quickly the water was increasing as we were backwashing, or flowing back through as we stop the backwash. You can get some general idea that there's a fair amount of water flowing through it, but we need multiple of these filters to accommodate this appropriately. So we're going to use a couple terms, loading rate or production rate. We're going to use these synonymously and call those VA, lowercase v, subscript A. This is matching with our book. Now be careful, because we're also going to look at volumes of water, which would be uppercase V. So we can define, for example, the loading rate as the volume of water per area per time. Volume of water going across that filter per time, which would be a Q. So volume over time is the Q that I was talking about here. And we're also going to say this is the Q for one filter, right? We have, if we're designing a treatment plant, we have a total flow rate that we need that's going to be different than the flow rate we're applying to any one filter. It's kind of obvious when I say it that way, but as we approach problems, we'll see that there can easily be some confusion as we deal with, all right, are we doing, like which Q are we solving for? And we just want to make sure we're not getting confused there. So we could add a F or filter subscript to that Q. Generically, Q is volume per time, right? So in the case of our loading rate, we've got that flow over that area, that's VA. We'll define a backwashing rate as well in a very similar manner. So we might want to put QF here, or we could say, if we're doing a Q total for a treatment plant, we could write it something like that. Total at the treatment plant, maybe. Regardless of how we want to describe it, just keep that difference in mind, right? We might be solving for a system, how many filters do we need, and we're figuring out, okay, there's this much flow for one filter, and we have to solve for 3 cubic meters per second total flow in the entire plant, right? That's the kind of thing we might have to do. So just keep that in mind. When we are dealing with the loading rate specifically, that's going to be a specific amount of flow to that specific filter. Got that? All right. So we have then a loading rate, a way to find it, simply the amount of volume of water we're adding to the filter per time, and divide by the total filter area of that filter. We can then get a term called filter efficiency, and this is incorporating all the water produced minus all the water lost divided by all the water produced. So this is just going to be what fraction of water that is passing through that filter ends up being clean and ready to use. So we're going to use this new term here and say this is going to be, on a volume basis, the filter efficiency. So it's kind of like usable divided by total across filtration cycles. Okay? So of course we recognize we have some rinsing time, so that's going to produce some volume of rinsed water that is not good to use, so it's going to waste. So if this is our rinse ripening stage, we can expect some portion of water that we need to subtract from the total there. During filtration or production, we have VF. And this is a very important thing to keep in mind conceptually, right? The only difficult part about the math here is just understanding what I'm talking about when I say VF or these different components. So the math is really, truly very simple, but keeping all the pieces in mind of where does this come from, how does it relate, that's where you have to pay some attention. So the VF, that's what we're getting as we're loading water onto the filter. Of course, we have to stop that during backwashing, and we're not taking production water when we're doing the rinsing, because the rinsing water goes to waste, so it's different than the VF. Then we can start, once it's clean enough, we can start taking it, and then we operate for some long period of time, hopefully. That's all our VF. Then we have to stop, we're no longer gathering it, and we do our backwash. So we might have a moment where we have an air purge here. There's essentially no water made or lost here. So I'm just going to say no water, right, if we do an air purge. And then we have a volume of water that we use for backwashing. All right? So through our cycle time, that's what we can expect. That's why we have in our filter efficiency the volume filtered minus the volume consumed for backwashing minus the volume consumed for rinsing, all divided by the total volume we did filter in the first place. Okay, so on a water efficiency basis, this is typically greater than 95%, or we'll say 90%. 95 might be typical. Maybe usually they're better than 95. Maybe we'd do an example where we did it at an at-home system and it wasn't very efficient or something, you know. But generally, in practice, these are going to be rather efficient. Most of the water they filter is going to end up as usable water. Now, when we have to find these volumes, right, we might have to solve the problem and figure out, okay, well, how much water did we use for this or that? It's very simple. Finding the volume is, well, what's the area of that filter? What was the loading rate? And we can do this all with units, right? We can do the units analysis. And how much time did we spend filtering? The only caveat here is that during backwash, we might change the rate. Maybe we double the speed for the backwash to really churn things up better. That's the only weird thing that might happen. So just take a note that we might have a backwashing loading rate. If you're not given anything at all about backwashing loading rate, probably just assume that it's the same as the loading rate. It can vary anywhere from the same to twice the speed. So we'll say backwashing rate or loading rate, VB, is anywhere from 1 times to 2 times VA. And it's, if you're not given any information, just assume it's VA. Of course, that means you have to read to see if it did give you any information, right? So don't jump to that conclusion, but that might be appropriate. Okay, the other thing to note here is you might have to convert some units, right? You might be given square meters for area and liters for, asked to answer in liters or something, or maybe your loading rates in liters per square meter. You might have to adjust some things as needed. Time versus loading rate, maybe you're answering how much time in hours or given time in hours, but you have minutes for the backwashing, but hours for the production. You know the deal. Just make sure your units are matching and you'll be fine. So if we take a look at this, just how I drew it to approximately to scale here, we know that VF is going to be rather large. VB and VR are going to be rather small, and they're probably about the same size. Maybe a little different, 20 minutes, 15 minutes, twice the loading rate, whatever. It's still going to be like, a couple hundred cubic meters here when we produced 10,000 for the filtration or something like that. Okay, so relatively straightforward stuff here. We just have to make sure to account for that and then put it all into practice. Now the next concept is to have a net loading rate. And this is going to be convenient so that we can get a net water produced over time or per time. So we have a loading rate, VA, for production, and now we need an effective loading rate. So we're going to say this effective loading rate, or REF, matching our book's nomenclature here. And we could describe this as, well, how much water are we effectively producing over the total amount of time we are producing the water, or over the total cycle time. So if we have a total cycle time, we can describe as TC, then that's going to be equal to the amount of time we spend doing rinsing plus the amount of time we spend doing backwashing plus the amount of time we do filtration and any time for air purge. So that's why we can simplify all of this stuff into TC. So when we derive this equation, it's pretty simple. We're just looking at that amount of water produced effectively, meaning subtracting all the losses, divided by the total cycle time. Okay, it's pretty simple to say it that way, and on an equation, it's going to look like this. Okay, we can take the volume filtered minus the volume backwashed minus the volume rinsed divided by the area of that filter times the total cycle time for that filter. All right, you'll have this equation and the other one on your next formula sheet. I have not yet updated that, but I will next time I get the chance. And of course, we can calculate the volumes accordingly, each of these volumes just like we were talking about. So putting these together, we can see that we get some value here now that on the net, we know how much water we'll produce given some filter area. And this is still going to be something like cubic meters per square meter per second, or liters per square meter per hour, or something. It's going to be a volume per area per time, just like the loading rate. Keep in mind that the effective loading rate is always going to be a little bit less than our actual filtration loading rate because we have these inefficiencies. Now, it might be tempting to think that the difference here is just multiplying it by that efficiency factor. And if you did that, you'd be kind of close. But given that there might be some time for air purging or some other maintenance, it's definitely not always the case. Only if we had exactly the same backwashing rate as loading rate, and all the time there's no spare time aside from, basically if there's no air at all in the cycle time, then maybe we get pretty much the same to say, you could, under those conditions, which are not normally true, you might be able to say the VA is equal to, the REF is equal to the filter efficiency times the loading rate. So don't do that, is my point, because it's not usually going to be true. It may be if you feel like it and you're thinking very clearly and understand this, maybe you could use that to check to make sure you're in the ballpark, because they'll be similar, but don't count on that, okay? Don't count on it to be exact. So use the REF equation here. It's just the net volume divided by the area of the filter over that total cycle time. It's not that complicated, and if you're solving for a nu anyway with this equation, you already have all of these volumes, right? So just keep in mind there's an equation for each, and to deal with that. Okay, so I'm going to have you do some practice here. Put these numbers into place and see how it feels to solve a problem. So we have an example here. It says a conventional water treatment plant treats 2.4 cubic meters per second of river water. So this is a flow rate for the entire plant, right? So we already see this is going to be Q for the plant. If I can find my... So for the entire treatment plant, there's our flow rate. The filters in the plant are 8 by 8 meters. So that's going to be 8 squared, 64 square meters of surface area. And they operate on the following schedule. A filter is cleaned once in each 24-hour period. And the backwash rate is 10 liters per square meter per second for a period of 8 minutes. It takes an additional 8 minutes to drain the filter and break up the media with air injection. Of the total filter cycle time of 24 hours, 15 minutes is used for rinsing the filter after backwashing. During production, water is applied to the filter at a rate of 5.5 liters per square meter per second. So the questions are, what is the filter efficiency, and what is the minimum number of filters required by the plant? Okay, so this is, as you see, there's going to be some steps here. I'm going to give you some time to think about that. I'll write these equations back up here for you in a moment, and I'll probably start, filling in pieces for you in a couple minutes. Have a second page if we need it. But this is a good example of the type of question you might face on a homework or exam, right? It's a little bit involved. It's going to check, can you solve this word problem in that way? Okay, so take some time. Feel free to work together, and feel free to ask me questions. I'm going to give you a bit of time to work on that. Question? Yeah. Okay, good question. So question is this 5.5 the loading rate? Yes. And what we'll see here is it says during production, which cues us into that's like when we're loading, when the loading rate is what we have, right? We are applying water to the filter at some rate. So that means that effectively the water is going to go through it at the same rate we're giving it to the filter because gravity is going to push it through. Like maybe there's a microsecond where it goes a little slower and there's some resistance and the water stacks up higher, but overall, if we're putting that much water to it, it's going through at that speed. So you'll see this guy, that's VA, and we're given a backwashing rate up above the 10 liters per meters squared per second. Yeah. Oh. All right, so I went ahead and put some numbers here if you want to check your first part. I've skipped a little bit of the unit conversions and direct calculations. I've got that in Excel. I can show you in a moment. But basically, to answer part A, we have to figure out, okay, well, how much volume did we filter and produce? How much volume did we use for backwashing? And how much volume did we use for rinsing? And to get those, we need some information about the loading or backwashing rate and the times used there, plus the area of the filter, of course, is 64 square meters. And then the first part of the question then is really, okay, well, how much time do we have for each piece? What's not given is the amount of time we were spending filtering, but we were given a total cycle time of 24 hours, and they were pretty clear about that in the text. So we can just take 24 minus 8 minutes, 24 hours minus 8 minutes, minus another 8 minutes, minus 15 minutes, and put all that in the same units, and we're good, right? And I think in Excel I ended up converting everything to seconds so that I could use the loading rate in seconds as well, because again, we have to have consistent units there. So once you do all that, you should get a volume of just under 30,000 cubic meters filtered and just over 300 cubic meters used for backwashing and rinsing. That puts you at a filter efficiency of just about 98%. Any questions or issues on that? Basically just put it in Excel here for each piece that I needed, and everything written on the sheet there is kind of what you see here. You guys want a few more minutes to do part B, or are you good to go? No answer? Good to go? All right. Okay, so then part B, we're looking at how many in total do we need. I'm going to give us a little more space. So we answered A. What are the minimum number of filters required by the plant? I'm going to call that number of filters. And the way we can approach this is to see on, like, effectively what's the flow rate or what's the production rate for one filter, and then take that and see how many of those filters would be required to get the entire plant. So we can say we probably want to find that effective loading rate. That's going to be the VF minus VB minus VR, which is a value we already solved for in part, divided by AF times total cycle time. We should have all of those pieces already, so that becomes, should have this here, .0527. Cubic meters per square meter per second. Now we can check to make sure this is lower than the loading rate, so we can convert our loading rate, VA, our VA, convert it to those same units, and that becomes 0.055 cubic meters per square meter per second. So we see that, yes, indeed, the effective is smaller than the loading rate. That's because we're averaging over more time, and some of the water went to waste. So that's good. Our effective has to be lower by definition. So we get that. Then we can continue on and say, well, our effective flow rate is going to be equal to, let's say the flow rate for one filter is going to be equal to the effective loading rate times the area of the filter. And if we look at the units here, that's going to work out very nicely, right? It's going to be very obvious to us. So the flow rate, let's say in cubic meters per second, would be very convenient to match the cubic meters per second given to us at the outset. So if we're leaving it in cubic meters per second for a flow rate, that's going to be, and our effective loading rate is cubic meters per square meter per second, multiplied by square meters for the area, then that's good news, right? That's, our units are all matching up there to cancel to leave us with cubic meters per second. Okay, so that's the process then. If we're going to do Q for one filter, we can do it this way. We could also say if we wanted to, the Q for the total plant, and then say, well, the total filtration area all together. So whichever way you want to slice it and dice it, it's just going to be algebra. Just make sure you're doing the word problem correctly in that sense, right? Are we solving for the flow rate for one filter and then multiplying that to how many we need, or dividing it? Or are we solving for how much total filter area do we need, and then divide that by the area of one filter so that we get the total number of filters? Really doesn't matter which way you think about it, as long as we're accounting for things appropriately. So if we do this, that should be 0.0527 cubic meters per square meter per second times 64 square meters. I'm actually not sure if I solved it this way last time I did it, so we'll see. And that should be 0.3372. Cubic meters per second for every filter. So then, approaching it this way, we can say we need a total flow is 2.40, and we can divide that by the Q for a given filter. Thank you. Like that? And it should be probably for both, right?
No, the effective was right.
So the effective needs to be lower. So if I was wrong on one, then I was wrong on both, is what I'm thinking. In my notes, I also have it. I must have it wrong also, at least written in my Excel notes here. There's no way that the loading rate can be 10 times smaller than the effective loading rate. That, unless I'm talking about maybe for the entire plant, but that would have, so whatever I have written here is a mistake. I know that. And now the question is, was the
Yeah, I'm sorry. No, you're right.
So which part? The way I have it written now? Okay, good. Okay, so we're gonna, so thank you for that correction and double checking that. The way, it's funny, the way you were saying it was the same way I had it written over there too. But okay, so that should be the correct thing. And if we take a look, really to convert that 5.5 liters to cubic meters, we're just dividing by 1,000. So it should move over 3 decimal places, which is what we did. Okay. All right, good then. And then I should also correct that here. Okay. I believe this should still be correct. Hopefully. So if we take the flow rate for the total plant and divide that by, what I'm going to write here is Q per one filter. When we divide it that way, or when we describe it that way, what we're effectively going to get is the total flow rate divided by the flow rate per filter, and so that per filter unit will come onto the top, and the flow rates will cancel, and we'll end up with the number of filters needed. That's the way the units will work out there. So the let me do it this way. Say, yeah, no, that's fine. All right, so then we're dividing that by the 0.3372. That will give us the number of filters should be 7.12, but we can't have 0.12 of a filter, right? So we calculated number 7.12 filters, but we were asked what the minimum number was, and 7 is not going to cut it, right? We need more than 7. So 8 becomes the minimum number. We have to round up in that case because we have to treat enough water, some minimum amount of water, and we're doing this in sets of filters that are 64 square meters, right? So if we rounded down, we're not producing enough water. So we round up, and that's a good thing, and technically we'd probably round up and then add some number of filters to give us extra capacity in case, we're gonna design in case we have to do excessive maintenance or something like that, right? We're gonna design for overcapacity. So in this case, we have almost one full filter overcapacity. Maybe that's good. Maybe this design criteria was already saying, so 2.4 cubic meters per second, maybe that was already the max load they project in 20 years or something. So maybe there's already that design factor in place and we're good with 8. Or maybe we decide, well, we don't even need 8. Let's cut these filters in half and have twice as many of them and then do like 7.5, so to speak. Whatever the case, there's our answer, and that's a good example of putting all these pieces together. Does this make sense? We good on this? Okay, so really I think the only complication is understanding the terminology, what it's referring to when it's saying water is applied to this or all that. Okay, so I think that's about it for granular filtration. One more reminder, I will post this quiz shortly for this reading assignment. It's posted on Moodle, and I'll skim through it with you real quick. It's actually a pretty interesting read. This is a sciencey paper, so don't feel like you have to read and understand every last word of this. But when you approach some scientific literature like this, good idea to get a basic understanding of it would be to read the abstract, flip forward, read the conclusions, maybe also stop. Typically the last paragraph in the introduction tells you kind of what really they did given the context that they just described. So reading the introduction might be a good idea as well, but this is a good place to scan in to see, okay, well, what exactly were they doing? They usually say that right before the methods. So examination of 2 plants, records on quality of untreated water and treated water, so before and after, and it revealed something about turbidity and blah, 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 blah. Okay, so without hardly touching the article, I already told you kind of what it's about, right? We're looking at a before and after for 2 plants and something to do with turbidity and what was going on. You could read as much as you want, and the other thing I would encourage you to do is take a look to see if the graphs, see if you can make sense of some of the graphs. It's another good way to skim an article for comprehension. See what they're saying. So this is a turbidity over time. And even without going to anything else, we can see there's a difference between the northern and the southern plant here. And the southern plant seems to be having some big issues during these moments, right? So at minimum, we have already learned something about this case study. We can also take a look over here. This is onset of this cryptosporidium illness. And again, we have it plotted by months and cases. So chances are good. There's going to be some correlation with that turbidity coming out of the plant and the cases here, right? So that's going to be part of their study in some sense. Okay, so take a look at that. It's not going to be a huge amount of time. That'll give a little more context for this. Okay, I'm going to move over now and go to membrane filtration. Okay, so we talked about this last time. We might have granular filtration as some sort of packed bed. We know about that now. Membranes typically are going to be different in that they're going to do the size exclusion. So physically separating the particles because they just can't fit. And if we think about it, we can do that for many sizes of particles, you could think of, practically speaking, a tennis court has some fencing to keep the tennis ball in, right? You could also keep a dog in with that kind of fence, right? And then you go down, if you need to keep mosquitoes out, you get a screen mesh for like a screen porch. You still want the breeze if you can, but no mosquitoes, right? We can think of what can we do physically to separate by size. If we go down small enough, we can start removing cryptosporidium, for example. A little further, and we can get rid of bacteria. Even further, we can get rid of viruses, and eventually we could even get rid of molecules, to the point where we can use membranes to even exclude large salt ions and do what we call reverse osmosis to desalinate water. Now, as we'll see, the smaller we go, the more pressure we have to add, which means the more energy, and of course these membranes get quite sensitive to things that could harm them. So typically we would do a series of filtration because we don't want large things damaging these very fine pores for the smaller stuff. Okay, so what is a membrane? And at this point, let me grab a piece of paper. I don't know whose or what this is, but it's a piece of paper. We can say a membrane is a bit like a piece of paper in the sense that it's the overall definition is it's something that kind of is a layer. It's typically pliable. It's something that's typically a sheet or covering or layer, usually from a plant or an animal is the context. And sometimes we might even call it like this piece of parchment or something forming some kind of a roll. So we can look at several different types of membranes for water treatment in that same manner. I'll probably come back, grab that again. And we can use them to treat water, right? I already kind of ran through these examples. We can remove particles, just like we can with the granular filtration. That we might call, and we'll see this again, we might call this microfiltration. In reference to a micron or a micrometer. So if we're on the scale of 5 to 10 micrometers, maybe a little more, that would be microfiltration. Now we might go further, get rid of a lot of colloids, pretty much all bacteria, and maybe even down to viruses. We would call it ultrafiltration. Going below that, if we're trying to remove chemicals, we're getting to the nanofiltration or reverse osmosis. And these are kind of blurred lines in many ways. So that's the thing. When we use a membrane that looks a little bit like a sheet of paper, it's just going to have pores that are so small you can't really see them unless you had a very fancy microscope, typically, right? And that's to deal with these very small contaminants. In terms of water treatment, membranes have not been used for a whole long time. Maybe the first time was 60 to 70 years ago, and really only became common about 30 years ago. So it's a relatively new technology. Of course, that's plenty of time to build up a good knowledge base for it. And they're not always the most price-effective technology. So if we can do sedimentation, if we can use granular filtration with no problems, a lot of times that's going to be what operators or designers will opt for. But you can save on a lot of space if you go for membranes instead of these big granular filters. And you can improve the quality if you had some particular concern that you needed to deal with. So there's certainly some applications, and if you had, if you had disaster relief scenarios or you wanted some at-home thing, emergency or even for a private well or something, a filter might be a pretty good option because you can set it up and have it as a relatively small thing that's self-encompassed, right? Okay, one thing to note about membranes is the pore size, the pores that water will go through that will block larger particles. That is has an inverse relationship with the pressure required to do it. This will make a lot of sense. If you think about it again tangibly, a fence, a chain link fence that you'd find at a tennis court, the wind can go through that with almost no resistance, right? Maybe if the wind's blowing really hard, you see the fence shake a little. If you then take a screen porch, you can realize, okay, that's actually stopping some of the wind. It's not as breezy inside that as it would be outside. It can still go through. Then if you take a parachute, well, you can probably push air through a parachute, very likely, but it's actually blocking a lot of wind as the wind's blowing through it. And it's very hard to push air straight through it, right? That's kind of the point of it. So you can imagine in the air, it's going to be very similar to liquid, right? It's going to depend on the viscosity, these pore sizes, all this stuff. Now, when we operate a membrane, we have a few terms that you'll need to get to know and get used to talking about. Permeate is going to be the water that has permeated through the membrane. It has gone through it, it's found its way through the pores, and now presumably it's cleaner. Occasionally we might have a condition where maybe not for water treatment exactly, or not very often, but maybe we want to keep this contaminant, or maybe it's a product. Maybe we are trying to harvest some algae and we push the water through and catch the algae. So maybe we are not using the permeate, although that should be cleaner in the sense of what we're doing. In a sense, if you ever see something from concentrate, that's going to be the opposite of the permeate, where we have a concentrate or a retentate. In the case of juice, you could filter orange juice and keep all of the concentrated stuff, all the molecules, the flavors, the fibers, all that stuff you can keep with less water so that you could ship it cheaper and then just add water and you have your orange juice again from concentrate. So a couple examples of when we might actually not be using the permeate exactly, but generally the permeate's what the clean water. This is treated. That's what we'll typically be using. So if we were to, I'm just going to draw a little cylinder and say there's a membranes in there. We would say we had feed and permeate. And then sometimes we will also have a concentrate flow where some of the flow is not passing through the membrane. It is being stopped by the membrane, but some of the material is going through the membrane as a permeate, but some of it is not, and it's collected as a waste stream or the concentrate stream. So in that case, let me draw this a little better. I'm going to just draw as if we had one flat sheet. Water's flowing by it. Here would be the concentrate. I'm redrawing it because I'm going to be particular about these drawings in here in a moment to be a little more specific how we can do a box diagram and all that to show this. This is just to show you that we have a feed, that's the dirty stuff, then we have permeate, that's the clean stuff, and then we have a concentrated amount flow if we're operating it in that manner. Okay, so those are the primary terms we'll have to kind of watch out for. And we have two ways of operating. I just kind of hinted at this a little bit. Typically, in practice, we'll do cross flow, meaning we have all three of those categories as flow rates. So we have a flow coming in, we have permeate going across this membrane. In this case, we see the membrane here, water is going through these pores, and we're rejecting, so we have a retentate here, or a rejection stream. And the point of doing that is so that we're not gathering millions and millions of particles that eventually just foul up the surface completely. Because if we didn't have any retentate, thered be no end to the amount of particles getting stuck, and then we'd just have to stop rather quickly. So instead of backwashing, like stopping operation into backwash, we can kind of continuously backwash by operating with a cross-flow operation and be collecting that more concentrated stuff continuously. So it's a lot like the granular filtration where we're going to have to do something with those particles eventually, but in this case, we can just take them out continuously. We might still have to backwash a little bit for the membranes or agitate it to clear off the surface, but it's more like seconds, like pump the water backwards through it for a few seconds to get it going. So it's not nearly the same scale of stopping operation. Okay, when we describe these then, I'm going to use these box diagrams to say, if I can find my cursor, if this is the feed, and I can draw a line here, a diagonal of some sort, to say the water's going to cross it or not to get past the membrane. So we could draw it this way, or we could draw it this way. I don't really care, but what you notice here, I've put 4 lines. Depending on which way we draw this, those 2 of the lines are going to be redundant. So in this case, if I draw it that way, this is the retentate. Because the water that's arriving here has not crossed through the membrane. Right? This is the stuff that didn't pass through. Everything else that passed through would be the permeate. So we don't need to draw 2 lines. We probably won't have 2 different lines. I guess we could. But whatever crosses that membrane in my drawing is now permeate. Okay? So we could draw this as like that, and that'd be fine. Right? Likewise, it would not matter at all if we drew it like this. In fact, if we draw it like that and we flip the diagonal, then we just flip the retentate and the permeate. Right? So just showing you this box diagram stuff. Don't stress about it too much, but make sure that the permeate's whatever crossed that line to understand it properly. Now, in a sense, if we, we'll talk about here in just a moment, the other way to operate a membrane would be to put a membrane here, or I guess you could just write it like this, and you have a feed and a permeate, and then no other flows. This becomes a dead-end flow, is what we call. I think that's the next slide. A lot of times, I'll just draw it like this, and then it looks a lot like a little syringe filter that maybe you've used in a lab where you push the water through and it's going through this little disc, and you can filter the water that way. So this is what I'm talking about. So dead-end filtration is the kind of the simpler form, but it's more like a batch process where you have to use that filter, and then eventually it's too clogged, and then you have to swap it or backwash it or whatever. So that's usually like a small scale system and not a continuous process. If we do that, if we flow some water through and stop, then whatever's left in here would be a concentrate, but it's not a flow. So we have to keep that in mind. If we're using a dead-end filtration, we can collect a concentrate, but it's going to be a volume and not a flow. Right? So this would be unless we add in another pipe to that system or another outflow direction, it's going to be just some volume there. The nice thing about membranes is all of this boils down to mass balances that are very, very simple. And that's because we're not dealing with a reaction. We're just dealing with some portion is separated. Maybe sometimes the most complicated thing would be, okay, only 80% of the particles are removed. But that's still a very direct mass balance to deal with. We're not creating or destroying any matter, so whatever's coming into the feed is going out the permeate plus the concentrate, or is getting stuck in the concentrate volume there. So it's going to be very simple. We just are going to have to handle some concentration changes like that. Okay, so we've got batch, kind of, which is called dead end, and then the cross flow. Another example, so the little syringe filter is a good example of what you might have seen in a lab. Likewise, you might have seen one of these guys where you put a filter right here, put some liquid here, pull a vacuum, and that's going to pull the water through the filter, and then you're going to collect water here as you permeate. So in this case, it might look like, and maybe you'll have some little collection vessel. It might look like we've got 3 flows, but in this case, really all the filtration is happening here. So this would be the feed. And then we have a filter. And since there's no flow coming out somewhere up here, since that does not exist, then it's just dead end. Right, so all we have is a feed and a permeate, and then we're just pulling air out of the vacuum. So maybe you've seen that before. Good example of cross flow is a little lab setup here. I found image online. What we have here is dirty water over here. This would be our feed. We've got it being pumped. Back here we've got a pump. And it's pushing water, applying it with some pressure to our membrane apparatus, or a membrane unit. And this particular membrane, you can kind of tell, we'll talk more about this mostly next time. I'll probably mention it here in a moment. This membrane, we have water flowing in, and then there's a pressure valve here. This is going to let some water escape, but force some water through the membrane. So in this setup, we are allowing some water to leave here. This is going to be our retentate. The rest of the water is being forced through this membrane. It's like a hollow tube. It's as if we have water flowing, our feed water flowing in, and a pressure on the other side, forcing water through the membrane. And so some of the water is escaping through the membrane, and we can actually see in this image, if you look closely, there's water accumulating. It's a membrane and then a clear plastic casing around it. And so you can kind of see some of that water accumulating right here. And so wherever the water escapes outside of that tube, it's being collected, and the only path for it to go is straight out here to the permeate. And what you can see here, again, if you look kind of closely, the feed water is clearly orange, kind of dirty. The retentate's hard to tell, but it should be dirtier, right? So it should be a deeper orange, more particles, more nonsense. And turns out that permeate's looking pretty clear, right? It's doing a good job removing those particles. So that's an example of what it schematically can look like in practice. And in this case, we essentially have, what I'll do is I'll draw it this way. We'll say, actually at our box diagram, it's going to be a little difficult. We have a feed, of course, and depending on where we draw that membrane, that's going to dictate what's permeate and what's retentate. The box diagram doesn't port very well here because what the image here looks like the permeate's coming down from the bottom, and it's just going to be a little, to draw that on the box is a little weird, right? So let's just say I draw it here. The one coming down then, that's the retentate. And this would be the permeate. So when I draw the box diagram, it is just that. It's a diagram saying, okay, when do we cross the membrane? Don't think of it as this is physically what it looks like, right? It's not, the box diagram is not a physical representation or not an exact. Conceptually, it holds true. The water that crossed the membrane is our permeate, right? Physically, how it ends up looking in practice might change. Okay. I think that's good for today. We'll stop there and pick up here next time. And well, we're going to go through the exams next time, so perhaps we'll finish up this after we talk about the exam. But we'll see you on Tuesday. Yeah. Yeah, I will put the grades on Moodle before class on Tuesday.